Right. Energy in simple harmonic motion. Okay. Um, Hopefully you remember from when we talked about energy that for a spring mass oscillator, the potential energy is most commonly the spring potential energy, which is 1/2 kx squared. Okay. Now, if you wanted to find the total energy in the or in a spring mass oscillator, okay, you actually could solve this at the end points of the oscillation, right? Because that's when all of the energy is potential, is the end points of the oscillation or the amplitude. So you could actually just use E total equals 1/2 Ka squared, where A is the amplitude of oscillation. Okay, so if you figure out the amplitude, you can use this because all energy is potential at the endpoints, or the amplitude, whatever you want to say, right? You can also use these two equations for energy. These are not as easy, but sometimes you are given, sometimes you only have enough information to use one of these other ones. At equilibrium, okay, all energy is kinetic, okay? So then you can say that the total energy would just be equal to 1/2 mv max squared, okay? So if you can find the maximum speed during the oscillation, then that's when all your energy is kinetic, and you can do that. Alternatively, and this is probably not the best equation to go with, this is probably the hardest one of all of them, is to say that I didn't even draw it. I didn't even do an A. At any point, okay, total energy is just the sum of the spring potential energy, 1/2 kx squared, plus 1/2 mv squared. Okay, so if you know the amount of if you know the spring constant, the spring stretch, and then or spring stretch or compress, and then the mass and the velocity of the block that's oscillating, then you can actually find the total energy at any point in the oscillation. Doesn't have to be in equilibrium. Doesn't have to be through any of the amplitudes. But if a system is exhibiting simple harmonic motion, the potential energy function must be quadratic. Okay. We did this, I think we talked about that in the very first section where it says that potential energy function must be quadratic for simple harmonic motion. Okay. So that just means it's going to look kind of like a parabola, right? Okay, and you can kind of see some of the stuff there. On the back side of this page, it mentions it kind of has a little blurb of text here. And basically, what's happening is that when you do a, you might have noticed that for the total energy, I did not include MGH. I did not include gravitational potential energy. And the reason for that is because you don't need to if you meet these certain conditions, right? So this is like the spring just hanging on its own, and this is its original equilibrium. Now, when I put the mass onto it, of course, the spring is going to stretch to support the mass, and there's a new equilibrium that we've reached. If we define x equals 0 to be the new equilibrium position of the spring mass oscillator, then we can define and we can also define the potential energy to be 0 point there. We basically can completely eradicate MGH. There's no need to have MGH there's no need to consider it because it's effectively we've effectively eliminated it from the problem, right? Basically, what we're doing is when we shift the equilibrium position, when we define x equals 0 to be the new equilibrium position and u equals 0 to be the new equilibrium position, we're basically taking, can you see this dotted line parabola? That's our original potential energy function, right? We're basically shifting the axes to be where what am I trying to say? Our parabola is now at the center of or at the origin of our axis. Okay. So this is my new potential energy. This is my new position axis. And so basically we've now defined we've basically shifted our origin point so that we can make the problem easier for us. There is a lengthier proof for showing that MGH actually cancels out if we make this our new equilibrium position. you don't really need to know it. If you want to find it, you can find it online. But really, it ultimately just shows that like um, that when you move it, MGH you can consider it. It's just going to cancel out. So there's not really a need to do that. Okay. Okay. Well, that's energy. Okay. I'll be back with small amplitude oscillations.